let's do it after the break or after we finish this. Okay, is this working? Seems to be. All right, let's begin talking about IV. Talk about it in a couple of different ways. So in the previous session, we talked about dealing with endogeneity by basically assuming it away, which is kind of what we do with all of our problems anyway. We just assume them away. And we're going to do it here as well, but with in a slightly different way. Okay. So begin with a slightly different version of what we were talking about earlier this morning. So we might be interested in some effect, but we might have another input. So here's a simple example with one outcome and two inputs. They might be dummies, they might not be, but for the purposes of this, they're going to both be potentially continuous. So we think that the outcome depends on two variables, x1 and x2. So here's a simulation idea. The first thing we're going to do is we're going to draw x1 from an IID distribution. Then we're going to draw x2 from an IID distribution. We're going to draw the error from an IID distribution. And then we're going to essentially take the data x1 and x2 and u, multiply it and add it and so on to get our outcome yi. And then we're going to estimate two different models. Model A ignores x2. Model B includes x2. So what do you expect to see when it comes to essentially comparing beta 1 and gamma 1? What do you expect to see here? What is gamma 1 supposed to be? Right, 2. Right. Minus 2 here, we expect gamma 1 hat, right, that to be minus 2. You think beta 1 is going to be minus 2 or something else? Yes, I'm simulating this model here, 4 minus 2x plus 0.75 x2. Okay, so I'm simulating that model based on x1, x2, and u being drawn from an IID distributions. So gamma 1, right, should match this. You know, with simulation error, right? What about beta 1? We're ignoring x2. You must have an opinion. You're not allowed to not have an opinion. This is basically a question about beta 1. Why?
I'm thinking x2 and LXM left it outside, right?
Yeah. I've estimated model A by ignoring x2. So I've created data that's based on this function. So I've simulated x1, I've simulated x2, and I've simulated u, right? I've got lots of observations, okay? My y is calculated based on this. Okay? Calculated y based on this. And I've run two regressions. One ignoring x2 and one not ignoring x2.
If it is not ignoring it, wouldn't it then be almost similar?
Meaning this one.
Estimate B.
Yeah. So estimate B, because this is essentially this regression, right? We expect gamma 0 to be around 4, gamma 1 to be around 2, and gamma 2 to be around 0.75. Okay. Everybody with me on that? What about beta 1? Where we ignore x2.
What do you mean? Isn't we just
Should it be the 2 or should it be something else?
less than 2? I think it's closer to 0.
Okay, why do you say closer to 0?
Doesn't what happens if x2 go into x1?
Okay, why do you say it should be close to 2? I have two opinions. The rest of you fail.
I just think
Huh?
I probably just think 2.
Okay. There's the estimate. It is exactly 2. Well, within simulation error. So even though I'm running this regression and entirely ignoring x2, I'm getting the correct estimate for x1. Why?
I think those who are substituting the t out of the outcome.
Not. I'm not substituting anything out.
Okay, but now I'm thinking, think that estimate A, the other term you really also ignoring it.
So the error term in model A has these two components in it.
So then you're in the other term. That's why,
But why should it just be in the error term?
because then it's the everything that you don't put in the model.
Mm-hmm.
It goes to
You sure?
there,
Right, right. But what do we worry about with the error? Then it's what? Our concern isn't that we're throwing it in the error. Our concern is that what is in the error is correlated with what's left over. Okay? Here, x1 and x2 are drawn from separate IID distributions, so they are not correlated. Because they are not correlated, running this regression is the same as running this regression if I don't care about x2. I will get the exact same slope because x2 is completely uncorrelated with x1, putting it in the error is fine. Okay? On the other hand, if I draw x1 and x2 from a correlated distribution with some sort of negative correlation and do the same exercise, what should I find? Yeah.
Related. No,
Yeah.
negatively correlated.
They're not negatively correlated? Right now, I don't care about direction per se. I care about what I should expect to see.
Does it become like more biased in other place?
Well, there was no bias before.
Well, now it comes.
Now it becomes biased
X1's correlated.
because X1 is correlated with X2. Depending on the size of the correlation, right, is the size of the bias and the slope, right? So here's the true fit. Here is the biased fit in terms of slope. Okay, so the slope estimate is wrong if I do not include X2, right? We call this omitted variables bias, and this is a form of endogeneity, right? So this is when we talk about these sorts of things like, let me jump ahead real quickly. When we talk about these things like here, right? If in this treatment example, I'll come back and redo this in a second. But if it's not correlated with what we don't observe, if there's no correlation here, we get unbiased estimates, right? Our concern is the opposite, right? That there is some sort of correlation between what we don't know, right? Everything, and what we can observe. Okay? When there's correlation here, this non-zero term here creates a potential bias, and that potential bias plays out here, right, with incorrect estimates of the slope parameter or the treatment effect. Okay, so let's now formalize that, go back through this story that I had this morning, but this story is worth repeating probably almost every day if you work in this space. You should practice telling it to your dog. Okay. All right. We've got a binary treatment outcome. An agent gets treated, some sort of education outcome, some sort of health intervention, whatever it happens to be. Okay. So D represents the treatment status. It's a binary dummy. And we have outcomes associated directly with this. Y1 is for D equals 1, and Y0 is for D equals 0. And in practice, the outcome Y is the weighted combination of the non-treated outcome plus the treatment status times the gap in outcomes. All right, so if D is equal to 0, this term goes away, right, and Y is equal to Y0. If D is equal to 1, we've got Y0 minus Y0, and we're left with Y1. Okay, so this is just a way of writing a regression, right? Before we didn't actually talk about regression. We just talked about treatment parameters. So now I've actually written a regression. I've got an intercept, I've got a variable, and a slope term. Right? The slope is the gap between these two. Right? So this is a very simplistic regression. It is an intercept, a slope term, and a dummy. But of course, because it's a dummy, it's not really a slope. But you know, that's not really the important part of this. All right? So I can write this as a regression. And now you can see very clearly the story we talk about in regression format, right? If this error term is not correlated with this variable, we've got an exogenous variable, and the regression on its own makes sense. All right, so that's what's on this next slide. I write down my regression, right, where beta is supposed to estimate the effective treatment, the difference in outcomes associated with the treatment, okay? And as long as that treatment is random, then these two are uncorrelated, and a simple regression of Y on a dummy with an intercept gives me the treatment effect. That's why everybody loves randomized controlled trials. They're easy. Right? But you have to get them right for them to be easy. As soon as you screw it up, well, then it's not so easy anymore. Okay. I wouldn't know. I haven't done either one, but I haven't done one, so I haven't screwed one up. Right? So it doesn't quite mean I can say I've done one correctly. All right. So, on the other hand, treatment is unlikely to be randomly assigned. We know that people choose to go to university. We know that people choose to migrate from one place to another, maybe in search of employment or whatever it happens to be. We know that we are economists. We believe people make decisions that are somehow good for them, right? So this is what we believe as economists. So we think that when people go seek a treatment, it's because we think that they want to improve something, okay? So we expect there to be a benefit in some way, and we call that a selection effect. Okay, so just another way of saying what I said earlier. We think of people doing things for their benefit or for somebody's benefit, and that's basically selection. So they seek the treatment, they take on the treatment because their outcome, well, it has something to do with where they are without treatment, but there's a difference between their outcomes with and without treatment. Right, that's sort of the simplest way to think about selection. All right, and so as I said earlier before we did matching, basically, if I'm just going to estimate an observed difference in the data, it's going to have two components. One is the effect I might be interested in, which is an average treatment effect on the treated, but it also includes a selection effect, and that inclusion of the selection effect, right, that's the bias. That's the wrong slope parameter because of the correlation between the error and the treatment status. Okay. So this is the picture we had before. Right? There's some sort of thing I don't observe. It affects the treatment status. It also affects the outcome. If all it did was affect the treatment status, no big worry. If all it did was affect the outcome, also no big worry. It's the fact that it affects both that causes problems. Because it affects both, I can't separate this part going into here from this part going into here, right? If this line didn't exist, it's not such a big worry, okay? Because that's exogenous D, right? Okay. So something unobserved matters in terms of understanding the outcome, and more importantly, something that's unobserved matters in terms of who's treated. And what we talked about this morning was that we would assume this away by saying, well, there's some things we can observe, right? Some X's that we can observe. And so instead of having unobserved confounders, we have observed confounders. And all we basically do is use them in a regression style framework. We create a propensity score. We use that propensity score to match the observations between treated and untreated, and we compare that difference across those, right? That's this propensity score matching theorem that basically says if the outcomes are independent of the treatment status given some set of X's, then they're certainly going to be independent of the outcome given some function of the X's, right? And that's where the propensity score comes from. And with the propensity score, now we can match on one single number. And once we match on that single number, we can easily calculate the average difference between the two groups based on them being similar in their X's, but the similarity is based entirely on the propensity score. Okay. Right? We had this balanced discussion, we had this strong ignorability assumption, and we had this overlap assumption. Okay. In practice, we do this via weighted regression because the weights are useful in terms of, well, weighted regression, it's easier to calculate standard errors than with matching. All right. So what we're going to do now is talk about proxies and instruments, talk somewhat about these sort of ideas in different ways. Right, so first thing I want to point out, instruments are great. They're flippin' hard to find. They don't just sort of fall from the sky and they land and hit you on the head and you say, ooh, nice. Okay? They're really hard to find. This variable, an instrument anyway, it must relate to our endogenous variable. It must not affect the outcome directly. And this is why sometimes these little path diagrams are kind of more useful than thinking about correlations. But because we have this new variable, we have a two-step estimator. But to be fair, matching is a two-step estimator, right? You estimate a propensity score, then you estimate the average effect from the match. Okay, so we're in this world where I'm kind of thinking about two steps. All right, so I'm going to begin with proxy variables, which is kind of how a lot of people think about instruments, but isn't quite an instrument. So what is a proxy idea, right? So we might think about a world in which we don't have the relevant information, right? This is this omitted variable idea. So we don't quite have what we want. So maybe what we could do is we could search harder, right? Let's just keep looking and keep looking. It's kind of costly, right? If your job requires you to publish papers, so you can't just kind of keep looking and never get anywhere. All right. It is possible that this sort of variable isn't going to have an identical observable counterpart, right? So a lot of the work we talk about when it comes to instrumentation comes out of labor and relates to education, right? So there's sort of a classic paper I'll talk about at the end that sort of puts some of this together. But it's hard to separate, for instance, education and intelligence, or ability and intelligence and education, right? So they're meant to be somewhat different capabilities, but they're not always sort of purely separable, right? So if the information is not properly measured or is not easily observed, it might be because it's difficult to measure. But in principle, what we're hoping is that the missing relevant information does not cause this sort of non-zero correlation, right? So what we really, in a great world, right? This is what we had a few moments ago. In a great world, right, this x2 is uncorrelated with the x1, so not including it doesn't cause a problem. It's unlikely, right? So in that world, we can just ignore it, right? If the relevant information is not correlated with what we care about, then it's okay. But that's not generally the case. Most of the time, it's going to be somehow relevant. So what we want to know, what is missing is likely relevant. It's likely correlated to our treatment status, and therefore we have to find some way to do this, right? So a proxy variable, which is different from an instrument, a proxy variable is often used to try to substitute for the relevant unobserved variable. All right, so this is trying to find some x, some x2 that's kind of like the x1, but isn't quite the x1. Okay? It's correlated with the unobserved variable, but does not necessarily belong in the actual population regression. Okay. So slightly turning the standard example on its head, we might say something like, all right, we would like to know how ability influences your earnings. We don't observe ability. we might observe your education. Okay, so in that kind of world, it might make some sense to use education as a proxy for ability. Okay, fair enough. And so this is one way to think about proxies. It is not the standard IV story that I'm going to tell you in just a couple of moments. Okay. But I'm going to use this thinking in a little while. So one of the things we're going to argue, right, is that ability is likely to influence your education. The more able people find education a little bit easier to accumulate. All things equal, right? So what we require is a variable that is directly measured, even if it's measured with error, that proxies for ability. This is not sort of directly measured. Right? So let's sort of this part. I know that education is probably, at least in part, it's determined by ability. I still think education could matter, but I don't actually observe ability. I don't observe actual ability. So instead, I've got this sort of latent, unobserved ability statement that I'm going to try to deal with in a moment. We've included experience to deal with some other features, but that might be a little bit too much extra information. All right. So what might people use as measures of ability? Well, we might have something like an IQ score, right? Or some other sort of test scores. And there's a literature that talks about using date of birth, but that's actually more of an IV story. Okay. So here, very specifically, we want IQ to be correlated with ability. So that this, if we were to run this sort of linear regression, remember, we don't observe this. Okay, so we can't really run this regression. But we want to think about alpha 2 as being some sort of estimable parameter if we had the actual data. And so the non-equal part here indicates that the latent variable right, and so this kind of scales across the different levels. So yes. I'll come back to that in a moment. Okay, but when a date of birth isn't thought this way, date of birth is actually treated as an IV. Okay, so I'll come back to this. Okay, but the idea here is that we're trying to we think ability matters. We don't have ability, but we're going to try to capture something that's like ability. Okay, and use that, and that's what then we think of as a proxy variable. Okay, so here is us replacing ability with IQ plus this parameter here. Right, the alpha 1 was the constant in the ability equation. Why beta 3? Okay. The education and experience part don't change. The beta 4 is the ability part in the earlier regression. The alpha 2 is the IQ part. And we've got this sort of this revised error term. And we've got this revised intercept as well, which is the initial intercept plus this beta 3 term, which actually comes from experience, and the alpha term from the ability component. And I think that's a typo. I think this should be beta 4 from the ability part of the regression from before. Okay. And then this error term, we have to adjust for the noise around the relationship between ability and years of schooling, right? So there's the V, right? There's the beta 4, right? So that term just takes on, right? So that's our new noise parameter, right? So our new regression is essentially income plus a constant that has a couple of components in it. Education, experience, and IQ, which also has a couple of components to it, and this new noise term. Okay. So it's still linear in the parameters, so in practice we can still estimate this. This is not particularly hard to estimate via ordinary least squares. What we need, however, to estimate that is for this error term to be well behaved, right? It needs to be uncorrelated with the other variables in the regression. Otherwise, this doesn't really work, right? So that's what we've got here. This new error term condition on the variables in the regression is equal to 0 as long as the underlying error term from essentially these two original equations, as long as this error term and this error term conditional on the same set of variables is also equal to 0. Okay, so we're basically making the assumption that we would expect, and that is to run this regression with this sort of proxy variable, we need some sort of measure of exogeneity of the new variables in the regression once we have it. Okay. So we get consistent estimates of beta 2 and beta 3. Unless we've got failure of that assumption. And so you get this sort of basic idea that if beta 3, alpha 1, and alpha 2 are positive, then delta 1 and 4 will be biased unless alpha 1 is equal to alpha 2 is equal to 0. Right? So this is a bad way of saying this, but we've got these different components here, right? And we want beta 2 and 3 to be unbiased. And so if this term here is 0, right, then that beta 3 component doesn't show up here as well, right? So that's what we're sort of worried about. So even when a proxy variable isn't perfect, meaning that there might be still some leftover correlation in the model, the estimates are still biased, but they tend to be better than if we didn't actually have a proxy. Okay, so here's an example sort of based on that. We're going to take log wages, the function of education experience, some x's and ability, where we've got this ability and IQ term. The x's are some characteristics, and we're going to expect that those characteristics are probably positively correlated with IQ. And so even if we have this imperfect proxy, which means that the V error term in the ability equation is not entirely 0 given the other correlates, right? So when that happens, ordinary least squares on this regression here, well, with IQ, I should say, ordinary least squares on that is inconsistent. But if IQ is a reasonably good proxy, the bias of an imperfect proxy can be less than omitting IQ, right? So here's this example we want to show. We've got an unobservable Q. We're going to include it in the error under the usual conditions, where there's arbitrary correlation between x2 and this z here, right? So the relationship, so I'm basically taking this ability equation here. Maybe I should have left it as ability and IQ, but I'm taking this sort of equation here as my proxy story, right? And this is kind of hard to see, but here is an estimator where I ignore the proxies. Here's the estimator where I include the proxies, and I've got slightly different versions of the inclusion, right? And what you see is, well, we don't really care that much about the constants. What we care about is, sorry, from the regression, should really be x4. Oh, well, he doesn't even give me these. Sorry. Okay, now I confused myself, which is always unhelpful. But, okay. Yes, what is that noise? Okay. Yeah, thanks. Okay, so sorry. So what we're trying to do here, and so this is less clear than it should be, and that's my fault. What we've got is two types of models. One where we estimate sort of the model where we've got the data as we need it. One where we've got the data where we've got a proxy for the variable we want. Okay. Here we actually have a really good measure of the variable we need. Here we have a proxy, and here the proxy is kind of bad, right? So the difference is between these sort of three models. Here's the right model. Here's the right model, but we don't have the variable we want, but we have something really close. Here's the variable where we've got some sort of proxy to replace the variable we want. But it's a well-behaved one, and this one has correlation, right? So the comparisons are actually 1 and 3, or column 1 and 3 and column 2 and 4, okay? So here, between sort of 1 and 3, we've got a decent proxy, and we get fairly close estimates. Right, this is x31, this is x3 star 1, right? So these are the same variables, but this is the proxy for that. And here we've got x32, but my proxy is poorly behaved, right? And what that happens then is I get the wrong estimate entirely for the variable of interest, and it screws up my other measures as well, okay? So you can get a proxy to work well sometimes, but not always, okay? So short answer, we really don't use proxies much, okay? Instead, what we try to do is make use of instruments. Right, so here's a slightly different version of the picture we had before. Here's an example where u and x are correlated with y, but there's no correlation between x and u. In this one, u and x affect y, but there's also correlation between x and u. Right? So that's the difference in pictures. Okay, and so the implication of that, again, we mentioned that this morning, the implication of having endogeneity is that my actual estimator is equal to my actual estimate is equal to what it should be plus something else. And that plus could be negative, of course, right? So it could be minus something else. All right. So even in a multivariable model, when there's only one endogenous variable, all of the elements can be inconsistent. Okay? We don't typically worry about all the elements. We typically only worry about one or two, right? Because we might care about the education effect, or we might care about the medical aid effect, or something along those lines. So a lot of times we don't sit and worry about endogeneity with variables that we're not really focused on in the analysis. Okay? But the point here is that it can, as it said here, right? The point is that this endogeneity can be smeared across all of the variables. Right? That's what they mean by smearing effect. This error can go up everywhere. Right? Like smearing peanut butter on bread. Okay. All right. So here's a picture of a proper instrument. Here's a variable z that directly influences d. The key point, not correlated with u. Okay, so because z influences d and d influences y, I can estimate what I care about and fix this problem. Okay? I don't have u, I don't have something that tries to replace u. I just essentially go through it. All right? Hopefully this becomes a little clearer. All right, so I'm going to use some path words in a second, right? So this is actually called a mediated pathway. D is the mediator between Z and Y. You might have heard people talking about mediation. Okay. D is referred to as a collider on a backdoor path. All right, so D to U to Y. And it's called a collider because, right, Z and U go into D at the same time, right? So if I want to go from Z to D to U, technically I can't because this pushes back, right? So it's like, that's what we mean by colliding, okay? And that collision is actually kind of important. So if we try to imagine a shock to Z, it's going to induce a change in D, right? So that's the easy point. So there's some shock here. That shock here pushes into D. But that shock has nothing to do with this part of what's going on, okay? It's just here. So there's that direct shock. It's going to push up D in some way, or down. I don't know which direction the shock is. So D is correlated with Z. And so in that sense, any change in sort of D and Y arises purely from the change in Z. Okay? So here's the thought experiment. I do something here. Not here. Here. I do something here, it goes through D and it changes Y. Okay? By doing that, I can now explain the relationship between D and Y. Right? Any shock to Z helps me understand what's going on between D and Y. Even though I've got this problem here, that problem goes away because I can control the shock in Z, as long as I have this so-called variable Z. Right? That's the real problem. So we've got two basic properties with an instrument. I haven't actually called it an instrument, but Z is assumed to be an instrument. It has to be uncorrelated with the disturbance. Sorry, this should be U, right, to make it clear from my picture. The epsilon comes from the previous equations, right? But there's we tend to go back and forth between U and epsilon and V. Okay, so exogeneity. It's obvious in the picture, so just a second. Z is uncorrelated with this term, right? That's what we mean by exogeneity. Doesn't matter here. U does not affect this, so sweet, yes.
So Z doesn't influence Y on its own. Only influence Y to B.
Yeah, that's actually another very important point. I think that's my next point on that slide, but yes, absolutely. Oh, it's not. It's one of these slides. Okay. So if we think about this picture and the shock example, right? Oh, wow. Brand new pen. Okay. So basically you get this change in Z leads to a change in D, leads to a change in Y. So this change is basically determined by this change. Okay? And so we talk about an IV sort of estimator. This is what we have here, where basically what we're trying to do is figure out the sort of overall change from Z to Y, and we're going to divide that by the overall change from Z to X. Right, so we're going to essentially pull out the ZX part from the overall Z to Y bit. And that's referred to as the IV estimator. That's the picture version of it. And of course, for this to work, it becomes very obvious when you write it in the IV estimation form. If this covariance is 0, we can't take that division. Okay, so we have to have relevance. Okay, so we have two assumptions when it comes to IV. One is the exclusion restriction, exogeneity. Z and the error term are uncorrelated. And the other is relevance, which is that Z and D in my picture or Z and X in general are correlated. All right? So again, it comes back to this. If there's correlation here, I can't run my thought experiment from here to here because I've got other things affecting Z. I'm going to isolate the change in Z so I can isolate the change in D, and that then isolates a change in Y. Okay? Now, I'll get to, I don't know which slide it is, so let me answer you now. Notice where the arrow doesn't go. Doesn't go to Y. Okay? Z is assumed not to affect Y directly. That's part of what makes it hard to find, yes. Okay? But it can't. Essentially, if Z affects Y, then in principle it also is going to be correlated with the error term. So you lose the exclusion restriction. Okay? It's somewhat easy to see in the picture because if I draw an arrow from here to here, then I can just as well draw an arrow from there to there to there. or from there to there to there to there, right? It goes all the way through. So I don't want that. So yeah, when we talk about the exclusion restriction, which we write often as this, right, that the error term, this U in my picture, is uncorrelated with my Z. That is exactly the same thing as saying that my Z is not directly causing my Y. Okay. And I know I have a slide in there somewhere. All right, so this is hard. So IV has been developed as a solution to exogenous regressors. But there's some fairly interesting history out there. There's a geneticist who did some work on trying to understand the relationship between parental height and child height, whose father, I think it was an economist. And what the economists sort of took some of the ideas from the genetics and turned it into this sort of paths to understand sort of what had to be true for us to understand what's going on. It's a fairly interesting set of things, but I suppose a bit off topic. So IV has been developed specifically as a solution to deal with endogenous regressors, right? That's kind of how it's always presented in the textbook. But it also helps us understand causal relationships, because we can, if we're interested in a causal relationship, we think that there's endogeneity, and we have a good IV, we can actually estimate the non-endogenous part of the causal chain. Okay? How can we get endogeneity? Well, through measurement error, through omitted variable bias, simultaneity bias. It's probably other ways that we haven't quite figured out yet. Certainly selection is a form of endogeneity. Right? So there are things that can do this. But yes, how do you find an instrument? Knowledge and luck. All right. But we're getting better at this, right? So a lot of natural features, geographical features, biological features, weather patterns. A lot of these are fairly exogenous, right? But they're related to things. So for instance, if you're interested in trying to understand the sort of endogenous bit between sort of mother's, we'll call it weight for lack of better words, and child birth weight. And child birth weight is actually a fairly important determinant to long-term health. You can actually you can control for the mother's birth weight by rainfall patterns before they were born and during their sort of early years, right? Because there's very strong correlation patterns between mother's weight and child weight, extremely strong correlation patterns. But some of that's endogenous because it's related to a couple other things you can't really control. But there's also really strong evidence over time that mothers who were born during droughts are smaller than mothers who weren't born during droughts. Right? So you can use weather patterns as instruments long term, right? There's this really nice literature out there on sort of long-term health impacts of weather, right? So those are useful. The other thing things that aren't here are, it's mentioned, right? Institutional and historical. These should actually be their own bullet points. So you can think about past events as mattering. So another bit of health work, right? I don't actually do as much health work as I want to, but again, there's so like the Spanish flu from the sort of 1914-20 range, right? That decimated populations. there's really strong evidence that the children that were in utero during that time frame have poorer economic outcomes as they got older, right? So they didn't get the nutrition they needed as babies, and therefore have not done as well later on in life, right? So those are sort of historical events. But the key to that historical event, right, it's kind of somewhat random, right? I mean, the flu doesn't sort of happen daily and sort of doesn't really impact everybody at the same time. Right, and it went around the world like numerous times. I think like 3 times or something like that. And then we have got institutional things, changes in government, changes in policy generally. There might be reasons for policy changes, but a lot of these policy changes are exogenous to the individuals, right? So, if an NHI ever happens, then the NHI is there, right? I didn't choose it per se; it's there. So I can think about that institutional change, that sort of policy change, as likely exogenous to decisions I might make. Okay. So this is a set of things. It's only a small set of things. Anybody ever heard of Josh Angrist? No. Okay. So he's an MIT applied econometrician who managed to get his hands on U.S. Veterans Affairs data. And of course, the U.S. has been in numerous wars. But what they did was they had, for the Vietnam War, they had a draft. And drafts come with randomized numbers and so on, right? So the randomization of the draft process itself created instrumental variables for analysis on the impact of various things on labor market outcomes over time, right? So it's, I'm not sure if that's all luck or if he knew the right people or what have you, right? But there are a lot of things that do happen that have these sorts of possibilities if only we could figure out how to open up the door, right? And, that isn't necessarily easy to do, but worth thinking about. There's a paper now that's almost 20 years old by Murray, Avoiding Invalid Instruments and Coping with Weak Instruments. That's a really nice survey on IV estimators. And what it basically tells us is some of the things I'm talking about. We have to try to be intuitive when we talk about instruments, right? So if you read a paper that uses an IV, a large share of the paper is actually focused on justifying the IV as meeting the exclusion restriction and the relevance condition. Right? If you read a panel GMM paper, they do nothing. They just say, oh, I just assumed that the Ariano bond conditions hold. Right? It's crap. Not because it's bad, but because there's no justification. Right? So there are assumptions within that structure. So now let's talk about whether or not those assumptions are realistic in the modeling structure you're dealing with. Right? And that, it sounds like I hate GMM. I don't, right? Two-stage least squares is GMM. So it's not that. What I despise is people not trying to justify their instrumentation structure, right? And it's not because they've got some Sergeant J statistic that justifies it. It's economic intuition and understand sort of implications of violations of those assumptions, right? This is what makes it hard, right? To do it really well, you need to dive in and you need to get it. And probably it's worth understanding how to simulate things. So you can see what happens if this assumption breaks down in the kind of data you have or something. Otherwise, you're going to have to really, really, really understand the theory, right? And sometimes that's hard to do as well. Okay. All right. So the point of this is that it's not about the technical details, right? It's not about, oh, I've made this assumption and so it's right. it's about what makes that assumption plausible. Okay. Immons has also a nice paper about this. And Josh Angrist as well, when a lot of his papers do a really nice job of describing these sort of IV stories. Of course, to him, everything is an endogeneity problem in need of an IV, right? Whereas some other people have a slightly different set of, this is how I'm going to solve a problem. All right. So IV is simply not a cure-all, just like everything else in life, right? There's no simple fix to every problem you might come up with, or have, I should say. Maybe I shouldn't go so far as to say come up with. There are people that, can come up with lots of problems. But IV doesn't really fix all of these problems. And that's because instruments themselves might not be doing what you think they're doing, right? And if you've got an instrument that's not valid, then your results aren't any good. And in fact, they're likely worse than doing the estimation without fixing it at all. Okay. Right, and you find instruments work in some cases. The same instrument might not work in almost entirely in the same example for a different place. All right. There's just, I don't want to say there's no rhyme or reason, right? There is, right? It's this sort of economic intuition. There's understanding the context, all of these sorts of things that are likely to influence whether or not the exclusion restriction makes any sense in the setting you're working with. If you've got weakly correlated instruments, that can also produce greater bias than if you do ordinary least squares without this, right? So the first starting point, even if you think you've got an endogeneity problem, you think you've got a decent IV, you really should do a standard regression. Show us what the baseline is, right? And then we can see sort of how much the IV matters or doesn't matter, or if the IV result isn't any different than the original ordinary least squares result, maybe it's not doing much as an IV, or maybe it doesn't matter because it's not really a problem. Right, so this is kind of hard. You can do a little bit of statistical analysis around IVs, right? People talk about J tests and talk about sort of endogeneity tests, but at the end of the day, an IV is assumed to be uncorrelated with the outcome. You can't really test that. And the reason you can't test that in any convincing fashion is because of this. Right? In a purely statistical sense, even if Z doesn't cause Y directly, the fact that it's correlated with D, which is correlated with Y, means that you will find correlation between Z and Y. So you cannot run a simple test of the exclusion restriction. So you're always stuck trying to argue the plausibility of the exclusion restriction. Right? That's where economic arguments become so important. So you're trying to advance maybe some theoretical arguments or generalized economic reasoning to argue for the validity of your instruments. You want it to be based, and so, right, depends on who you're talking to, the audience that you're dealing with, whether or not they find these sorts of arguments plausible or not. Right? So you might convince an argument in this, you might convince an audience here that this is perfectly plausible, but then you go somewhere else, you might not convince the audience that the same story is plausible. Right? Everybody has sort of different views of how the world operates. Right? So you're not going to convince every person of the same thing. All you can do is try your best. If, on the other hand, you have multiple instruments, right? So this is the one place where, sort of Ariano bond is kind of nice, right? Because you have plausibly large sets of instruments. You can test for over-identification. The idea there is basically that if I have two instruments and they both give me the same result, then you can say, okay, cool, I've got plausible story here. And the usual argument is, well, if the two instruments don't give me the same result, then maybe I don't have very good instruments, right? But that's actually not true. Because there's a slightly different development that argues that, in fact, the IVs that you use, if you have different IVs, they're probably doing something slightly different. All right, so again, let's go back to this picture. All right. Z1's influence on D might be entirely different than Z2's influence on D. Okay, so that doesn't make them invalid instruments. It only means that the underlying relationship is different, so that when you apply this instrument or that instrument, you actually identify different patterns in the data. Right? So if anybody ever heard the word LATE, local average treatment effect. Okay. So the whole argument behind the local average treatment effect is that the instrumental variable's estimate identifies the outcome that is caused by this chain that we were talking about. That Z has some influence on D, and because Z influences D, that influences Y. Okay, so this idea, let me try to say it slightly differently and I'll come back to you. So the late estimator, the local average treatment effect, says we've got some sort of, let's call it rainfall, right? We've got rainfall happens and it influences, and our interest is in how rainfall influences treatment status. All right, so maybe going to the hospital for, I don't know, I'm getting tired as well. So the treatment effect that we identify is the treatment effect that says that rainfall is actually causing the change in behavior that's causing the change in the outcome that we observe. If we've got a different instrument, which is about thatched roofs, right, then that instrument, right, thatched roof is changing D, is changing Y. All right, they might both be instrumenting for the same Y or the same D, but they're not going to have the same impact because they affect different people differently. Okay, so that's what we mean by local average treatment effect. It is only the instrumental process that matters. So these over-identification tests are also generally viewed as less important than they used to be. Yes?
My question is there a limit of how many IVs you need in your equation?
Is there a limit? A limit to how many you need. Okay, so the simple answer is that you should have an instrument for every endogenous variable you have. All right. If you have more than that, great. If you have less than that, well, then you aren't going to deal with your endogeneity problem. All right. So if you have one instrument for every endogenous variable, we call that just identified. There's one for one. If you have more than one, then it's over-identified. But as I said, over-identification might actually just be you've got multiple pathways that the instrument works, or that the treatment works. Okay. All right, so did I think I jumped ahead too quickly? Yeah, all right. So if we're going to overcome criticism, We need diligence concerning omitted variables or other forms of endogeneity, right? So how are we dealing with this? How are we describing this? What are we doing to convince the reader that we've done as much as we can, right? So IV estimators are also biased in the presence of omitted variables that matter, right? This is maybe fairly obvious, but if you've got other forms of endogeneity that the instrument doesn't deal with, then the IV isn't going to fix the underlying problem, right? So maybe we need additional controls. Alternative instruments, right? So you can, this is sort of related to this is related to the over-identification story, right? If you've got multiple instruments, you can sort of add them in different combinations and sort of see how the results move. Okay. And then Art Lubell has one version of a whole series of possible options. And here the idea is that in standard IV estimation, the IV is based on a first moment, and in these sort of other things, the IV is based on a second or maybe even a third moment. So you look at the variation in the data, or you look at the skewness or the kurtosis of the data, and you can actually use that as an instrument in your analysis. Okay, so I'll talk about Lubell's method because it's fairly understandable. Some of these other ones are a little bit less so. Okay. So this is sort of a practical discussion. Right, this is the answer I gave to you a moment ago. Right, a model is under-identified if the number of instruments is less than the number of endogenous variables. It's just identified if the number is equal to, and it's over-identified if you've got more instruments than endogenous variables. And all of these relate to what are called order and rank conditions, right? So in order to get estimates, you really need to have something that's at least full rank. Right, and so if we don't have full rank, we don't get identification, and so on. Right, so this is fairly standard across all of these. All right, so two-stage least squares and IV estimators are special cases of GMM. Right, and I remember I told an author once that was using two-stage least squares, and I mentioned somewhere GMM in my correspondence with him. He says, "Oh, you're a moron. You don't know anything." I said, "Well, actually, I know at least a couple things, but this is one of them, right?" So these are all sort of special cases of subsets, right? So GMM is the sort of big picture, and notice they call it method of moments, right? So I don't really have this slide, but and my pen doesn't work. Or maybe the glass doesn't work. Let's blame the glass. There we go. So here's the exclusion restriction is essentially this. That the instrument is uncorrelated with the error term. Okay? So if you've got a linear equation here, right? So you think of y equal, say, x beta plus u. So you can replace this. Right, replace the error term with where it comes from in the regression format. You can work this out. You basically have a fairly simple statement. I forgot this part. Okay. So here's the assumption. This is the exclusion restriction, that the instrument is uncorrelated with the error term. And that gives me a very simple estimate for beta. It's basically Z transpose Y and Z transpose X inverse. Looks a whole lot like the OLS estimator. Okay, so I'm just quickly going through matrix notation, but it doesn't show up very well, so I don't want to spend much time. All right. So here's, I guess it's some of it's here. All right. Large sample IV. That's, yeah. So this is the estimator I started to write on the board. It comes from this idea that this mean, this mean is 0. It's Z times U is and it's an expectation, right? So it's just a simple mean. And if I rearrange that, the estimator is basically this bit. It looks a whole lot like the OLS estimator, except I've got a Z here instead of an X. And it is consistent by assumption, right? Where this assumption is that the Z is uncorrelated with the ERSA. Okay. It's asymptotically normal. On the other hand, if I do the two-stage least squares estimator, it's different. It's written the same way, but it's different. And that's because, there should be a hat here as well, sorry. The X hat is the first stage. It's the regression of Z on X. So my IV estimate is in fact not the same thing as my two-stage least squares estimate. If I compare ordinary least squares with IV, requires a bit of work, but basically the variance for beta 1 from the IV is some function of the variance of Z and sigma squared, and as divided by the covariance of Zx squared, and it's also a function of n, right? So you rearrange these sorts of things, and you end up with a very basic statement like the following, right? And this is what people often don't entirely understand, right? So let's first notice this bit. So the correlation between X and Z is the covariance between X and Z divided by their variances times each other and the square root of that. Okay, so that's a simple definition of the correlation. And that correlation is down here in the denominator. Correlations are never greater than 1. They go from -1 to 1. They never exceed that value. So we are always dividing here by a number that's less than 1, right? And it's squared, so it doesn't matter if it's negative, okay? So the variance in IV is always, not just sometimes, always greater than the variance in ordinary least squares. Okay, why is that happening? Because we've got this first stage where we regress X on Z, which creates some noise. And then we take that fitted value and regress that fitted value on the Y. So that noise gets carried through. So we get additional noise in the second stage that we wouldn't get if we just regressed X on Y. So if you don't worry about the equation so much, as long as you understand the idea. Okay. Variance of the IV estimator is always larger than the variance of the OLS estimator. And in many cases, the variance of the IV estimator is so much larger that you can't rule out the OLS estimator as being correct. It used to be very common for people to write in their paper, oh look, the IV estimator is bigger than the OLS estimator, so that means it had bias with ordinary least squares and that the IV fixed the problem. But they didn't actually pay attention to what happened to the standard errors. And the standard errors were such that they hadn't really shown us much because the OLS and the IV estimators covered a very large share of the same set of possible parameters, right? Because of the standard errors and the different estimators, right? You actually couldn't rule out OLS. Okay. You can rewrite this in a couple of ways. This is also kind of useful, right? So if the explanatory power of the first stage regression is low, right? So this R squared is low, then the variance of in the second stage is expected to be way larger than it is for OLS, right? So you can think about this as, right, if your first stage correlation is poor, this gets even worse. Okay. IV is consistent. OLS is inconsistent as long as we have correlation between the x's in the error term. And so the opposite is also true, right? So that the stronger the correlation between z and x, the better off we are with standard errors, right? And so you can ask a sort of dumb thought experiment, right? If the instruments were the actual x's, right, then I would get back the actual ordinary least squares regression, and I would get back the ordinary least squares variance, right? And x is perfectly correlated with z because they're the same thing. Okay, that's the ideal, but of course, they're not the same thing because I'm using z to instrument for x because I think x is correlated, and so the correlation between those is somehow less than 1, and we end up with a bigger spread in the estimates. Okay. That relates to this point here, which is having weak instruments. And so the weaker the instruments, weak meaning correlation between x and z, the weaker the instruments, the higher the variance in the IV estimator. And it can even increase the bias caused by invalid instruments even in large samples. So if you've got decent instruments, and I'm going to use that word loosely because how you define decent versus weak is not entirely obvious, okay? But decent instruments, then as the sample size gets bigger, we're in better shape. But if we have weak instruments, it doesn't matter if we get more and more data, we still have bias. It just doesn't go away. So you can rewrite this in a couple of ways, but we'll end up with this one. The probability limit of the IV estimator is the real estimate plus the probability limit of the correlation between z and u divided by the correlation between z and x times their relevant standard deviations, right? So if we've got non-zero correlation between z and u, right, so we've got sort of imperfect instruments, or the correlation between z and x is quite small, the IV estimator is actually more inconsistent than the OLS estimator, right? And that's obviously a worry, right? That's why people pay so much attention to justifying their choice of instruments. Okay. And in small samples, IVs aren't great. Right? So even in small samples, it leads to misleading results. It gets worse, obviously, if we have weak instruments. Right? So, Angerston and Kruger have this 91 paper where they look at the relationship between their instrument is actually date of birth, and that's used to explain years of schooling. Okay? And they've got some 300,000 observations, and yet inference isn't always reliable. Right? And when n is that big, you almost always expect to see statistical significance. Right? It's just almost unheard of that you don't get it. So there's probably some problems in their paper with weak instruments. Certainly if you have weak instruments, the small sample bias gets worse. You've got bad estimates, you've got bad standard errors. It's like garbage 1 plus garbage 2 equals lots of garbage, right? So you got to be really, really careful with instruments, right? We tout it as the solution, right? Every econometrics book you'll ever see spends lots and lots and lots of times, lots and lots of space on IV, right? Because it's kind of all we have. We've got a problem. Let's imagine a way to fix it. This is the way we've imagined to fix it, and it's not exactly perfect if we don't have really good instruments. And even then, it's not perfect, but at least it's decent. There's another way to describe the bias. I'll skip past that. All right, but let's just summarize it briefly here. The bias rises with the number of instruments. It rises with the correlation between the residuals. So between the so if the X and Z is noisy, the noisier that is, and that's correlated with the sort of first stage endogeneity, right? That increases the bias, and of course, weakness of the instruments. That's the low R squared in the first stage. Stock and Watson argue that if you don't have an F, I think it's an F stat around 10 or more, then your first stage is too weak. But yeah, small samples make this worse. And adding instruments typically reduces the standard errors, but that doesn't actually work if you've got weak instruments. All right, so that's sort of a brief summary. It's really not always the case that we have more instruments. But one of the things that happens in two-stage least squares, let me just go back to this version of the equation. All right. One thing that happens in two-stage least squares, we're actually using the x's as instruments for themselves, right? So if you ever run two-stage least squares, you always include all the x's, always. It's not appropriate to run two-stage least squares and not include all the x's in both stages, right? You'll get the wrong answer, okay? And that's part of why some of this discussion is part of why, right? So by using all the x's, you're sort of adding additional instruments, you're improving the quality of the standard errors at the very least.